Okay then. So we are back now and we will start with today's session. Cool. So so did you guys remember whatever we have learned yesterday? I believe you should. Okay. So I
Yeah.
kind of gave you a homework question. How many of you tried at least multi BFS one, the thief and the policeman to write the entire code?
I haven't written, bro.
Okay. Others?
Oh, no, bro.
Mm-hmm. Manan, did you try?
No, no.
Hey man, you guys are having holidays.
Saturday, Sundays don't happen. Weekdays only it can happen.
So at least try tomorrow morning. Okay,
Yeah, yeah, huh. Hmm.
Yeah.
cool. So, what we'll be doing today is we will learn something as bipartite graph. Okay. Now, I guess I have gave a bit of introduction on this in our starting session. Okay, what's a bipartite graph? Do anyone remember?
Two nodes can't have same colors.
Exactly.
Right.
Correct. So two adjacent. Okay. I mean, with a proper definition, it should be adjacent. Okay. Given something like this. Okay. So the thing is you have to color you have to color this graph using two colors such that none of the adjacent nodes have the same color. Okay, let's try to color it and let's check whether it's possible or not. So since let's say if we are going with red, we have to do it with blue. If we are doing it with blue, we are doing with red. It should also be red, right? Now what's the problem? So
Blue.
if I
That will be red again.
color blue here also, I should have color blue. But if I color blue, you see the adjacent nodes are having same
Same
color,
color.
right? So this is not possible. Okay, this is not possible. So so there are some graphs for which this is not possible. Okay, now what happens is whenever you're giving an online assessment or a question, they directly won't ask you that given a graph, check whether this is bipartite or not. Bipartite means, let's say if you are able to color the entire graph using two colors following the condition whatever we discussed now, it's a bipartite graph. Okay, otherwise it's not. Now what we will do is we will do the same question, but let me frame the question in a different way. Okay. Say these nodes are there, right? These nodes are nothing but these are uh, school school childrens. Okay, and this represents a connection, that is these guys are friends. Okay, these guys are friends. Now let's say there is a sport event going on. Okay, there is a sport event going on. The guy who is supervisor, he just comes in and he tries to create two groups of people. I mean two groups of students. Okay, group one, group two. Okay, so what he tries to do is each of the students he has to assign into some groups. Okay, the condition is in each group no one should be friends. Okay, I mean none of the people who are in the group one or in the group two, none of the members should be friends with each other. Okay, is the question clear, understandable?
Yeah.
Quick yes if you guys understood.
Yeah. Hmm.
Yep. So this is what we have to do. Now this is the question given. Now can you see this is same as bipartite itself? Like check whether a graph is a bipartite or not. Because now what we have is we have students who are being friend with some people, right? Who are friends with some people. Let's say this is student one, student two, up to some guys, right? So now what we need to do is we need to divide them into two groups such that none of the members in the same group are friends together. Okay, this is the question which is given to you. It's your responsibility, or it should come by the learning or the observation that this is same as checking whether a graph is bipartite or not. Okay, did in the question did I mention even the graph? No, right? I just mentioned students and their friends. Correct, students and who are
Yeah.
members, their friends. I never mentioned this is a graph problem, right? But again, this comes from this observations. Like as you go forward you kind of understand that okay, this falls into the graph realm, and you kind of solve it whether this graph formed is bipartite or not. Okay, so this is the question. Now a very crucial observation is in this graph, is there a cycle, whatever it
Yes.
is on?
Yes.
Yeah.
And what's the length of the cycle?
6.
Yeah.
One, two,
Two,
three,
three,
four,
four,
five,
five,
six,
six,
seven. It's
seven.
not six, right? It's seven, no?
Yeah,
Okay.
7 edges.
Right? It's seven. So it's a seven length cycle. Okay. Remember
Mm,
this point very carefully because this comes in handy. Any graph which is having a cycle of odd length cannot be bipartite. That's for sure. Okay. Any graph which has a odd length cycle cannot be bipartite. Cool.
mm.
ठीक है?
Yeah.
So with this observation, let's try to do. Okay, we will do a simple DFS and just check whether it's bipartite or not. Okay, very simple. Now you remember, right? What there can be multiple components. Like it's not like we will have only a single
Yeah.
component, right? So this is a graph given to
The
us.
single component. Yeah.
What we need to do is we need to check whether this graph is bipartite or not. Okay, so let's try to do. Okay, what we will do, we'll try, let's say we'll start with color. Okay, say color
Red.
0. ठीक है, तो कलर 0 कर दिए. इसके बाद, so is the intuition very clear that whatever we are coloring to, its adjacent node should have a different color, correct?
Yeah.
So
Yes.
color 1, color 1. Now this guy should have the color
Zero.
0.
Zero.
Okay, this one, let's say color 0, color 1, color 0, color 1, color 0. So it's kind of like we are able to do the coloring for this, and it's a bipartite graph. Okay, so what we will do is we will do a regular DFS. Okay, we will start from any random node. Let's say node number 0. This is node 1, node 2, node 3. Okay, we will start with color 0. What we will do, we will go to adjacent nodes and we will color it up. Okay, and as soon as we see that uh, if someone is already been colored and if it has the same color, then we will return false. Okay, so probably we should go and see a bit of code. I mean, it's very easy to understand. Nothing fancy in this. Okay, so let me write it quickly. So is the intuition clear, by the way?
Yes, bro.
Yes, bro.
Got it.
What Manan bro? We are saying bro.
Ah, yes, Abhishek.
Okay, and we have the main method. We just paste this stuff. What information do we need? Uh, so maybe we will use a color array. That's it, right? Static int color. Okay, and we will take few of the information from here. Okay, so what we have done is our let me a general import. Okay, so we have taken the graph. Okay, initially, can I say all my nodes are uncolored? Can I say that?
Yes.
Yes.
So what we will do is maybe we can use something as -1 maybe to indicate that nothing is filled.
Hmm.
ठीक है, straightforward, nothing fancy. ठीक है, उसके बाद you remember, right, what we do for DFS? We start from each of the node. If color of I equals to -1, we need to do DFS. Okay? Boolean is component by partite. Okay, and we will write a DFS function which will take node and we will start with color 0. Okay, this is the color I am passing. Is it clear?
Yes.
Yeah.
Yes, bro.
Okay, if
Yes.
it is if it is not bipartite, okay, we can use some variable, probably boolean is graph bipartite. So let's assume that it's bipartite. Okay, if it is not, if this component is not bipartite, is graph
False.
False.
Bipartite is false, and we will break it up from here. Because nothing to check, right? Going further, try to check if we have.
Yeah.
And finally, let's system.out.println is graph bipartite. Okay. Now we are only left out with doing a DFS function,
DFS.
and I guess it should be pretty easy for us at this moment. Int node, int
Color.
color, uh, let's say call, because color is the array
Mm.
which we created. Okay.
Okay.
Okay, so as soon as we reach what's the thing we have to do, I mean, we
We
know
just change
since we are
update the
already
color.
coloring this, so this is what we do.
Call.
Now
Mm.
for integer neighbors, so we will iterate on each of the neighbors. Okay,
Neighbors. Get
if
code.
my neighbor, okay, if my color of neighbor is equals to -1, that means what's the meaning of this, that we have not colored this, correct?
Not colored.
So if we have
We'll
not
do
colored,
color.
please go ahead and color this with, can I write this? 1 minus call. So do you
Yes.
know this technique? I mean, it's very easy to switch between 0 and 1. If you keep 0, it will become 1. If you keep 1, it will become 0.
Mm.
Okay.
Yeah.
So 1 minus whatever, it becomes the opposite of that. Okay. Is it clear?
Yeah.
Okay.
Yes.
So Boolean, since it is a Boolean, right? It's not void. It should be Boolean, right? Because we are returning
Yeah.
true or false. Correct. Boolean check. Okay. Now, if check equals to false, what does this mean? It's a not a bipartite.
Yeah.
Correct. It's not a bipartite. If it's not a bipartite, please go ahead and
Return
return false.
false.
Okay. Clear, Avilash?
Else. Yes.
Hello. Else,
Yeah.
we need to do one more check, right? If it is already colored, if it is already colored and it is nothing but color of node, what should I do in this condition? What should I return?
Return false.
Exactly.
False.
Is this,
Mm.
see, agar ye if loop is not being executed, then it will come to this else if, right? What do you mean by else if?
Mm.
That if your neighbor has already been colored and it's the if the color is same as my current node, then they are matching, right? And if it is matching,
Mm.
then we need to return false, so we will return the false.
Correct.
Yeah.
Neighbor checking.
Yes, if everything is good, if everything is good, please go ahead and return true. Okay,
Mm.
right? And
Yes.
that's
Mm.
that's it. And if you run it and you see, we, we should get perfect answer. Let's see. Okay, we'll run it for two of them. Let's try to run on this. Okay, how many nodes? 4, 8, 10 nodes. Okay, 10 nodes. And uh, please remember this: 0, 1, 1, 2, 2, 3, 0, 3. कितने edges है? How many edges? We didn't calculate that. 1, 2, 3, 4, 5, 6, 7, 8 edges, right?
Yes. Yes.
Yeah.
8 edges. Okay. 0, 1, 1, 2, 2, 3, 3, 0. ये वाले 4, 5, 5, 6, 6, 7 उनसे 4,
Mm.
5, 5, 6, 6, 7 and
Eight.
8, 9.
true. That means we are able to do it, right?
Mm.
So we are getting, it's a
Yes.
bipartite graph. Let's check for the anti-test case also. Let's see whatever we have taken here. Okay, how many nodes? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 7, 7, I guess, right?
Yeah.
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 And please someone remember this.
8, I guess.
Is it 8?
Okay. Okay. Zero indexing, right? All right.
7 nodes, 1, 2, 3, 4, 5, 6, 7. Okay. So it's just a
Okay.
random cycle, right? So 0
Yeah.
is
Got it. Got it.
there. So how many edges?
Mm. 7.
And one more. Do we have one?
60.
60.
60.
Hmm.
Are we getting false? This is
Yeah.
expected, right? Because it's not a bipartite.
Yeah.
Okay. So remember
Mm.
this term that whenever you have some kind of connection between people or some entity, okay, and if they ask you to divide into exactly two groups, the first thing should come into your mind is bipartite. Okay. Clear?
Hmm. Yeah.
Yes.
Chalo, good. And it's a it's a useful tool. We don't know when it might appear. Okay, so it's better to keep in handy, right? Okay. So this is something about bipartite. Okay, now let's probably move to next concept. Uh, what shall we take? Okay, so yesterday probably forgot to take this, and it is something very important.
Topological sort.
Topological order. Okay. Now topological ordering, right? So what's topological ordering? Okay, let's take an example. Okay, and I would like to open this. Maybe we'll get some information. Topological sort. Okay. So can you guys read this statement probably? If you are done, please let me know. Okay. I'll also explain it from my end, but please.
Yeah.
Others?
Yeah, done, bro.
Manan, are you okay?
हाँ ओके बट कुछ समझ नहीं आया.
Okay. See, there is a directed graph given to you. Okay. And what they are saying is, agar there is an edge between u to v, okay, let's say 5 and 0, there is an edge, right, between 5 and 0. So in this
Hmm.
case,
Yeah.
I, ek, we will write some linear ordering. Ordering means we will write a sequence of these nodes such that 5 should always come before 0. Okay. तो जहां भी pointed है arrow, it should come later than जहां से start हुआ arrow. Okay. So
Correct.
see this case 3 and 1. So 3 should come before 1. Can you see this?
Hmm.
Think about 4 0. 4 should come before 0. Is it coming here?
Yes.
Right? 2 should come before 3. And we are getting that, right? So
Yeah.
topological sorting or topological ordering is something as that given a directed acyclic graph. Okay. Now why it's acyclic, we will see it why it's not. I mean, there shouldn't be any cycle in that. Okay. So it's a directed acyclic graph, and what you need to do is you need to print a linear ordering of the vertices such that always u should come before v in the order. Okay.
Hmm.
Now how this comes in the again in the online assessment or in some kind of test is. Okay, so a very famous question for this is something as course schedule. Okay, which is there in lead code. I
Hmm.
will probably paste that. But
Hmm.
course schedule is something that, let's say there are these courses. Node 5 is a course, node 0 is a course, this is a courses. Okay, and there is a prerequisite in the sense node 5, that is course 5, you have to complete before starting course 0. Course 2 you have to complete before starting course 3, something like that. Okay, what
Yeah.
you have to find it out is like, given some courses and their schedule to you, can you complete all the courses or not? Okay,
Hmm.
is the question clear, others?
Yes, bro.
Yeah.
Manan?
Yes.
Okay.
Yeah.
Okay. Okay, let's take this. This is a good graph, we will take this as example. 504. Okay, 504, 231. Okay, 2 3 1, and we have 4. Okay, now So there's a very famous algorithm for solving this topological ordering. Okay, there is something Khan's algorithm. Okay, Khan's algorithm, which will help us to find the topological ordering of this graph. Okay, now did you see the term DAG, that we can only solve it when it is a directed acyclic graph? Correct. So why can't we
Yes.
Hmm.
solve on a cyclic graph? Okay, let's take a very small example and try to understand. Okay, I mean it's very intuitive, but again, you
It's like you won't meet the condition,
yes.
right?
So can I say zero should come before one?
Hmm.
Yes. 201.
Exactly.
One should come before two.
Yes.
Yeah.
But two is also saying, but two should come before zero. But how is that possible? It's not possible, right?
Yeah.
Yes.
So that's the reason topological ordering only works when there is a DAG, because
Okay.
Okay.
you cannot kind of write a sequence which is dependent upon something and it itself depends upon something else, which in turn creates a cycle and you have this contradiction, right? One is saying that okay, 2 should come after me, 2 is saying that 0 should come after me, but 0 has already been come, right? So there is no way that you can create a topological ordering for this kind of graphs, so it only works for DAG. Cool. I hope this
Yes,
is
bro.
clear. Okay.
Yeah, got it.
Yes.
Yeah. So let's try to understand what I mean, this algorithm helps us, and probably we can use this algorithm going forward also. Okay. I itself used in couple of contests, I believe, Khan's algorithm. So it's a nice one to learn. Okay.
Hmm.
Now, what Khan's algorithm states is, okay, we need a Q data structure to solve this problem. Okay. So what it asks, okay, one second. Yeah. What it asks is go ahead and create an in degree for all the nodes. Okay. Go ahead and create an in
Hmm.
degree for all the nodes. So do you guys remember in degree in the
Yes,
Yeah.
number of
The number of
Yeah.
edges to
edges coming to the particular node.
yeah.
and we have five. Okay. So in degree of zero, how much?
Two.
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 One.
One, two,
Two.
one.
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 Can I say this? 4, 5 ko there
Yes.
is
Yeah.
no in degree, so I kept it 0, 0. Okay. So what Khan's algorithm will state is, okay, whichever the nodes are having in degree as 0, please take them into consideration. Okay. So what we will maintain is we'll maintain a Q data structure. Okay. And we will push all the nodes which are having in degree as 0. Okay. So currently, can I say my node 4 or node 5 are having in degree as 0?
Yes.
So we will push this
Hmm.
into Q data structure. Okay. Now we will pop it up. We will print also because we need an ordering, right? So let's print it.
Yeah.
Okay. Now what we do in Khan's algorithm is go to your adjacent neighbor. Okay. Go to your adjacent neighbor. Okay. Whatever the edges you see, right? Visualize that you are kind of removing this edges. Okay. You need not to actually, but like you have to visually, you have to kind of have a visual that you are removing this edge. Okay. So can I say if I remove this edge, node 0 will have only one in degree now?
Yes.
Yes.
Can I say node 1 will have only one 0 in degree now? I mean 1 in degree, because this has
Yes.
already been removed, right?
Yes.
Yes.
Okay. Is it clear till here?
Yes.
Chalo, theek hai.
Yeah.
So node 4 has
Yes.
been done because I don't see any more neighbors. Okay. So node 4 ka kaam khatam. Let's pop out node 5. Okay. Node 5. Okay. So we are at node 5. So can I again do the same visual that we will remove this? So can I say now node 0 has in degree as 0?
Yes.
Yes.
If it becomes an in degree of 0, please go ahead and add that. as
Okay.
simple as it is. Okay, okay, so
Yes.
5 का क्या है, 2 है, ठीक है, तो please remove this. We have 2. So what's 2? 2 ka in degree is 1. We will make it 0. Since the in degree of 2 is 0, push it. And do we
Hmm.
see any more edges?
No.
No. So we are done.
No.
No.
Now what's again? We have 0 coming up. तो भाई 0 पे जाते हैं. Do we see any more further edges?
No.
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 Nothing. Okay. Please go ahead and pop 2. 2 के पास कौन कौन है? 3 है. So go ahead. Okay. So 3 ka in degree is 0 now. So we will add 3 over here. Okay, now there are no more edges from 2. Okay, now the next element which will be popped out is 3. Okay, so you see there is only one edge going out. Okay, so we will make our one in degree of 1 as 0. We will push
Zero.
it, and finally I guess we are done with this, and we will remove one. One आ गया, one का there is no outgoing edge, and you see you got some ordering, and it will always be a valid ordering. Okay, and if you see, I guess this should be one of the answer, 452310. So we got in some other, I mean there can be multiple possibilities. Okay, it's not a single, there can be
Yeah.
multiple possibilities.
Yeah.
So is the intuition clear?
Yes.
Yeah.
What this
Yes.
algorithm states is that as soon as you take out any node, since you know that for this, let's say you are here, okay, and there are some dependencies, can I say all these three nodes should be here and this node should be here? I mean, it should be prior to this nodes, right? So after processing this itself, process this node. This is the simple strategy of Khan's algorithm. Okay, but yeah, since we are learning it for the first time, it's a good algorithm too. Okay, so let's quickly write the code for this. Can you guys write it, or what do you say?
No, we'll write. We'll write it.
Okay, Khan's. I just need to show one thing. Okay. I mean, I'm writing the code because I'll ask you another example probably for you guys. So,
Hmm.
Khan's algorithm, guys. Okay, so we have things ready with us. Uh, what do we need?
In
Degree.
degree. Degree है. Next we need degree Q.
Yep, also need a Q. So I'm removing this line because now it's a directed acyclic graph, right? So when it's a
Directed
directed
cyclic.
graph,
Yeah.
there should not be any bi connection now. Okay. Now, what do we have is we created this. Go ahead and have a Q. Okay. So do you remember what we need to do? We need to uh, make in degree
I
values feasible. I mean, we need to create an in degree, right? So can I say in degree of v plus plus? Can I say this? U से लेके V पे there is an edge. So V will have one in degree more, right? Does it make
Yeah.
sense? Okay. Now,
Hmm.
what we'll do, we will iterate on each of the node. Okay. And we will check whether if in degree of I, can I say this?
yes.
चलो ठीक है. If done, जब तक empty नहीं है, okay, go ahead, remove this. Okay, let's probably print this up. Okay, and then for integer again neighbors,
Adjacent. Dot node.
in degree of Neighbor
No.
minus
Neighbors minus minus
Minus.
0.
Add to queue.
nice. Okay, I put that's all. Nothing else.
Mm.
Oh,
Okay. So probably let's try to run this. Okay. We'll take the small example itself. This one. And how many nodes? One, two, three, four, five, six. So there are six nodes. How many edges? One, two, three, four. Are there six edges?
Yes.
6. Yes.
And 504052. 504052. 233141. 233 आ गया.
Hmm. 45023.
Yes.
Did we get this?
Mm.
Yes.
Okay, nice. So now we got some linear ordering of vertices, right? So till now, did you guys understand there can be multiple solutions?
Yes.
So if
Yes.
there are multiple solutions, I need the lexicographically smallest one. I mean, I need the smallest ordering of vertices. How to do that? Think for a couple of minutes and tell me. What I need is, I need, but there can be multiple solutions, right? So I need the one which is smallest. Smallest means the smallest number should come first, like that.
Priority queue.
Nice, good answer. So if I replace this queue with priority queue, then is my answer done?
Oh, yes.
Correct, right?
Hmm.
अगर priority queue लगा दिए, then can I say my answer is done? Because priority queue, it will always remove the smallest
No.
element, right? Correct? It will always remove the smallest element, right? So that's it. If I create a priority queue instead of queue, then we are done. Okay. Now the only thing is there would be a little bit of complexity because how many of you know that there is a complexity involved in adding and removing elements? So what is the time complexity of adding and removing in normal queue and priority queue?
I have no idea.
Adding is
Adding
n.
O of n in
Alright.
priority queue.
Normal.
One O of one node.
O of 1, no. In normal
Hmm.
queue, it's O of 1. In removing
Mm.
also, it's O of 1. But in priority
Exactly.
queue, it's log n. Okay. Log of,
Because it will be sorting, right?
no. Actually, what happens is you maintain a CBT, which is not CBT, I guess. It's binary tree internally. Okay. So
Okay.
maintain some kind of, tree. So it has to order something. So it takes a log n time. Okay.
For removing, right? For
Yeah.
or adding, it's big of one only, right?
Uh, I'm forgetting that. I completely forgot. I guess it should be login. Okay. But yeah,
Okay.
Forward
please
queue.
have a look.
Yeah. Yeah. For sure.
Yeah. Okay. So is it clear? Priority queue लगा दिए तो game खत्म. मतलब we are done with that,
Mm.
right? And we have solved this. Okay. Now, can you? So did yesterday we discussed one question, right? Uh, detect a cycle, print any cycle. Do you guys remember that?
Mm.
Yes, bro.
Yeah.
Now the question was there was one more question, right? That check whether there is a cycle or not. We used one variable, correct?
Mm.
Huh.
Yeah.
इसमें ना अगर if all the can I say if there is a directed acyclic graph, okay, if there is a what do you mean by directed acyclic graph? There is no cycle. If there
Cycle.
is a cycle, can I say this algorithm won't work?
Yeah.
Yes.
If this algorithm don't work, can I say there is a cycle? Simple, right?
Yes.
What we'll
Yeah.
do, int node count. Okay, we will count the nodes which are processed. Okay, so as soon as we remove, नोट काउंट कर देंगे. ठीक है. If node count is not equals to n, can I say there is a cycle? Did you guys understand this?
Yeah.
if
Yeah. The
if there
total number of
if there is a
nodes.
cycle, then this algorithm won't work, right?
Mm.
This
Yeah.
algorithm doesn't work.
Yes.
That means we will not have all the nodes, correct?
Yeah.
So
Hmm.
if we don't,
Yeah.
so
Hmm.
using one simple Khan's algorithm, you solved this many problems.
Hmm.
Okay, so this is a very powerful technique and it's very easy to write. See, this is it, and I guess you can also write it very quick, right? Within couple of minutes, not even couple of minutes. क्या है रिमूव करो गो इन डिग्री पे जीरो बनाओ अगर है तो ऐड कर दो दैट्स ऑल
Yeah.
simple as it is.
Yeah.
So you have solved one more problem that if there is a given a graph you need to check whether there is a cycle or not. Kant's algorithm is the one which can easily help you to go ahead and do that. Clear?
Yes.
Yeah.
Yeah.
Okay, chalo. So
Bro, can you quickly run this program with the priority queue? I want to see the answer.
okay, sure. So we have priority queue ready, right? Okay.
Yes.
Hmm.
So we'll run this. So shall we take the same example?
Yes. Yes. Yeah.
Yeah.
I mean, like, yeah, I was thinking of this. Okay, let's run it again now. Okay, 6 6. So do you remember 40, right? 40 50 4050 522331
2, 3, 3,
522331.
1.
So in this case, this is the smallest ordering. That's okay. I mean, there is no better answer. But yeah, since priority queue will always remove the smallest one, right? So you kind of you're ensured that you will get this only. Okay. Because let's say, uh, okay, if you just need to visualize, okay, I can do one more quick thing here. Okay. No, it should be linked list, right? Okay. Let's say we will go from the right order.
I minus minus.
Okay. Yeah. I minus minus. Okay. Come on, man. Why this doesn't get copied? So now, Sas, did you see we are getting 5 initially?
Yes. Yes.
And now again, if I replace this, if we replace this with the priority queue, and if I run the same program again, now can you see we are getting 4, not 5 now?
Yeah. Got it.
Got it, right? So
Yes.
priority queue, since it gives you the smallest, we are always in a right path. Okay. So stopping for this session.
Yeah.